Welcome to another IoT Central workshop. Please send any questions you might have in the chat. We will follow up with any unanswered questions using the email address you registered with. My name is Shawn Hymel. I'm a developer relations engineer with Edge Impulse, and I'm going to talk to you about performing inference using custom sensors. Now that we have trained a model using custom data from those sensors, we're going to deploy it to an Arduino board, and I'll show you how to do that. And we need to keep in mind that we've performed standardization in the past, so we have to do that again when we're performing inference. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of ML tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to nearly any device. You maintain control of the data and firmware the whole time. The Edge Impulse Studio is an online platform that handles everything, including data collection from your embedded sensors, labeling the data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is known as an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware, or a library, that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. In a previous workshop, we saw how we collected data from raw sensors. In this case, we were using accelerometer and a gyroscope. And then we needed to perform feature scaling in order to get that machine learning model to train in a reasonable amount of time and improve our accuracy. To do that, we performed something known as standardization. Now, we could have done normalization, but since the data was Gaussian, we ended up doing standardization, where we find the mean and standard deviation and use that to scale the data so that it was centered around 0 with a standard deviation of 1. Keep in mind, since we did that for our training data, we have to continue to do that for our inference data when we go to deploy this model. So we're going to collect raw sensor data. We are going to perform feature scaling using the mean and standard deviation that we calculated in the previous episode. We're going to send this now scaled feature set to our model to perform inference, and then we get those results out. Once you have those results, you can then do something with that. Say, for our magic wand, you make a gesture and then you light up something, or you, I don't know, change the channel, whatever you want to do with this inference results. With that, we're just going to do a very simple repeat. We have the inference results and then just go back to the beginning where we collect that raw sensor data, perform feature scaling, and then perform inference. In a previous workshop, I showed you how to use Colab to perform standardization with some raw data that we collected for our Magic Wand project. And for this, I'm going to be using an Arduino Nano 33BLE Sense, just like we did last time, with a button hooked up so that we can press it when we want to record data. Once we curated that data, we uploaded it to this Edge Impulse project, which I'm calling My Magic Wand Standardized. If we go into data acquisition, you can see where this raw data is. I'm going to select beta. This is one of the gestures that we drew, and you can see the data has been standardized, so it mostly resides between 1 and -1. That's a standard deviation of 1 with all of the means around 0. So you can see we have accelerometer as well as gyroscope data. I have gone ahead and trained this machine learning model, so all we need to do is just put in a raw data block. We've got accelerometers XYZ, gyroscopes XYZ, and then we put in a neural network classifier. This performs the feature extraction in Edge Impulse, but it's just raw data. All it's doing is just passing that data to our classifier. So we don't need to do anything here, but in our neural network, this is what I have set up: a dense layer with 80 neurons, a dropout layer, another dense layer with 40 neurons, and then another dropout layer. This seems to create a decently accurate predictor for the Magic Wand, around 95% at least for this validation set. So feel free to play around with this, but this seems to work well enough for my use cases. And there are other IoT Central workshops if you want to see how to set up training and test your data set. So I won't go into that here. What I want to focus on is this deployment phase. So I'm going to do it with an Arduino, but note that you can do it with a C++ library or any of these other supported libraries. The C++ library means that as long as you have a C++ compiler and the model will fit on your board, you can run it on just about anything. So I'm going to select quantized. I'm going to keep Eon compiler on. I'm going to build this, and I'm going to wait a moment while this completes. When it's done, you should be able to save the Arduino library in your downloads folder. And we are pretty much done with that. Open up Arduino and go to Sketch, Include Library, Add.zip library. Then in Downloads, find the library that you just downloaded. So this would be EI My Magic Wand Standardized. It's going to be prefixed with EI dash for Edge Impulse. So this is the one we just downloaded. So I'm going to open that. Down here, you should see library added to your libraries. And I'm going to copy and paste code in just to make this go a little faster. At the end, I will show you where you can have access to this code if you want to dissect it on your own. So we want to include the library My Magic Wand Standardized Inferencing. And then we are going to include the Arduino LSM9 DS1. This is a 9DOF IMU, which is a combination of accelerometer, gyroscope, magnetometer. We're just going to use the accelerometer and gyroscope from this. This is going to look very similar to the code we used in a previous workshop where we pulled in raw data in order to record it so that we could perform curation and eventually model training. Next up, I'm going to define some settings here. I'm going to use pound define so that they are more or less globally set and it doesn't matter what type they are. The button I have defined here is tied to pin 2. So I'll hold it up here so you can see what's going on, and all I did was just tie one end of the button to pin 2 and the other end to ground. So when I push the button, that pin will go low, and that's how we start the recording. I'm also defining the LED pin here as pin 22. That's the red LED on that RGB LED. You can set a threshold if you want to perform some action. This is saying that the confidence level should be over something if you want to perform a particular action. However, we don't necessarily need this because we're just going to print to the serial terminal so you can see what's going on. Then we're going to define some constants here. These should look very similar to the ones we did during data collection, where we want to convert to meters per second squared. We want to define our sampling frequency, and then from that derive our sampling period. This should end up with about a 10 millisecond sampling period, which should give us 100 hertz, and that needs to line up with how we captured the data. Otherwise, this is not going to work very well. Then I'm going to define our number of channels. This is our 6 channels, so this is X, Y, and Z for the accelerometer and the gyroscope. The number of readings we expect to get, so how big is that buffer? And remember that we want a 1 second buffer, so that should be 100 readings as long as we have 100 hertz sampling rate. And then we have our number of classes, which is 4 classes. So that's alpha, beta, gamma, and unknown. These are the gestures you can create with the magic wand. If you're wondering where these other defines are coming from, if I go into my Arduino libraries, and if you download the C++ library for Edge Impulse, this will be more or less in the same space. I'm going to go into My Magic Wand Standardized, Source, go into Model Parameters, and then Model Metadata. And I will move this window around so you can see it. And we are looking for EI classifier raw samples per frame. So I'm just going to search for that here, and you can see it here. And sure enough, that is 6. And then classifier raw sample count, that's 100. And then we have our label count, which I'm going to grab from here. So 4. This entire header file with all these defines is pre-generated, or it's generated by the Edge Impulse Studio. It knows to grab these from however you set up your project. So when you uploaded those original samples for our training set and our test set, it counted that there are 4 unique classes, and that's how this particular value gets set. And similar for the other ones, it looks at our data to determine how they should be set. So this file is automatically generated. which is why I recommend, if you can, pulling some of these pound defines using these constants rather than trying to define them your own, because that way, if you update your project with, say, additional classes, you don't have to change much in your inference code in order to make it work. That's why I'm using these pound defines here. Next up, we have our means and standard deviations. This you need to pull from that original Colab script that we were working with. So if it's saved, feel free to scroll down where it spit out these means and standard deviations. So we're just going to copy these. Otherwise, you'll have to recalculate them if you don't have these still from that Colab. So I'm going to paste those in there. And then I'm going to paste these standard deviations in here. Next, in setup, we're going to do the normal Arduino stuff of enabling our button pin. We're also going to enable the LED pin, and we're going to set it to high. Remember that these RGB LEDs are active low, so high means actually turn the LED off. We'll also start the serial port so that we can get some debugging information. Just like we did when we went to capture data, we're going to start the accelerometer. Just like we did when we went to capture the data, we're going to start our IMU. It said accelerometer initially, but it's more than that. It's also the gyroscope. Now that everything is set up, we can go to our loop and define some variables for us to use. So we're going to need our IMU data. This is the 6 different channels from the accelerometer and gyroscope. We'll need a timestamp in order to sample appropriately from our accelerometer and gyroscope. We'll store our results in this particular struct. We'll have error codes to deal with. We want an input buffer that is this DSP input frame size. And if we go back and look at this header file, you can see that it's a calculation of our sample count, which is 100, times our samples per frame, which is 6. So that's a total of 600 samples. That lines up with a sample rate of 100 for 1 second is 100 samples, and then 6 channels gives us 600 samples or readings. Next, we're going to wait for that button to be pressed, and then we're going to turn on the LED to show that we are recording. Then we're going to loop through these number of readings, which should be 100 readings. We're going to wait for that button to be pushed. When it is pushed, we're going to fill up a buffer for 1 second, and then we're going to use that buffer to perform inference to get results before repeating the whole process, which is why we're in this loop function. Then we are going to get our raw readings from the accelerometer and the gyroscope. Just like we did when we were collecting data initially, we need to convert our accelerometer data from G to meters per second squared. So this should all look very familiar from that particular episode. And then this is where we perform standardization on our raw readings. So we've got our accelerometer data, which is in meters per second squared, and our gyroscope data. We're going to subtract out the mean from our means array, which is right here. So this corresponds to accelerometer X, Y, Z, and then gyroscope X, Y, Z, and then same for our standard deviations, which is another array. And then same thing, we divide by the standard deviation in that array I just showed you. Then we're going to fill the input buffer with the standardized readings. Recall that the order is accelerometer X, Y, Z, and then gyroscope X, Y, Z, and then we go on to the next reading. So that's why you will see this index increment by I. So for each reading, up to 100 readings, it will fill in that slot and interleave the channels like so. Then based on our sampling period that we've set, we wait for a period of time, which should be about 10 milliseconds, depending on how long the rest of this takes. Then we will get out of that for loop. Next, I like to turn off the LED to show that recording is done. Then we're going to use this edge impulse function signal from buffer in order to wrap it into this signal struct. So we've got our raw buffer that we filled up here. We're going to wrap it in this signal struct, and this function just helps us make this signal struct out of it. Note that we also need to give it this input frame size constant. It's always a good idea to check your error codes. So if our return error is not 0, throw some sort of error and let us know, and then get out of this function because we don't want to do anything knowing it's bad data. Finally, here comes the magical function. This is where we actually run inference. Note that any processing in that DSP block we set in our project is run here, in addition to sending the output of that to our model to have inference performed. In this case, we pass it the signal, which we've set up in this function. This is an output, so our results are stored here. This is the output of our inference. And then false is debugging. So you can set this to true if you want some of the internal functions in run classifier to spit stuff out to the console for you. This helps you figure out what's going on if you run into problems. Finally, we are going to print these results. Note that it just goes through the number of labels, in this case should be 4. And then to get those results, note that this result is a struct, so dot classification. So classification 0, 1, 2, 3 correspond to each of those classes. We get the label, and so that should be constant, that shouldn't change. And then we can also do the same dot value to get the inference results, or the confidence score, or essentially probability, that the model believes the input data that we captured belongs to this particular label. And then, of course, we want to make sure that the button has been released for a few milliseconds before starting the whole process again, because we are in that loop function. Make sure that your board is plugged in. I'm going to select Arduino Nano 33BLE, select the correct serial port, and click Upload. And this will take some time to upload, especially if it's your first time trying to upload it, because it has to compile the entire Edge Impulse library that we downloaded. Once the uploading is complete, hopefully you see no errors in our output here. Let's open our serial monitor. It should look something like this. I'm going to take my Arduino board here, or my magic wand. I'm going to push the button, and then I'm going to draw a shape in the air with the board, and that'll give us the inference results on the monitor. So here we go. I'm going to start with alpha. And I did not draw that well. I'm also not holding the board correctly. It needs to be kind of flat, because that's how we collected data. Let's try this again. There we go. I need to draw a little slower. Okay, there we go. That's how we draw our alphas. You can see alpha being predicted at over 0.9 something. So it's really sure that that alpha is correct. I was drawing it too fast earlier. Let's try the other shapes. So beta. There it is, beta, gamma. Gamma, that's 100%. And then, I don't know, holding it here steady. It doesn't know what to do with that. So you can see unknown is pretty high when we don't do anything. If I do something else wonky with it, it really doesn't know. So that comes high. So that creates a high unknown confidence score. You can see up here when it didn't know what to do. This is where setting that threshold, remember initially we saw the threshold of over, say, 0.8. If we set that and say, oh, we're looking for, I don't know, alpha to be over 0.8 or gamma to be over 0.8, none of these would trigger that. So you could say, oh, is gamma over 0.8? If so, turn on a light, change the channel, whatever, right? There's your simple threshold. Otherwise, don't do anything because we're not sure, or the model's not sure that that's what the data was. If you'd like to take a look at this code and try it for yourself, you can head to bit.ly/IoTC-magic-wand-inference. So if you go here, it's a GitHub gist with the code that we just looked at and uploaded to our Arduino. So feel free to give that a shot, and I hope this helps you create your own magic wand or getting started using custom sensors with Edge Impulse. I want to thank IoT Central for hosting this workshop. You can find more workshops and Edge Impulse microsessions at iotcentral.io, where this video will also be available on demand starting tomorrow. If you have any questions about Edge Impulse, or you'd like to show us something you've built using Edge Machine Learning, please create a post at forum.edgeimpulse.com.